continue with the problems. Okay, so we're done with that particular sample problem wherein I recorded only because of the length of the solution, and I could sense that 1 hour will not be enough if I will be disturbed when my daughter keeps asking questions from me. So this one would be shorter compared to that one, so we will have this problem now. Okay, so for this slide, the last two topics will be discussing liquid metals. So liquid metals are also used as heating mediums in heat transfer, or that is forced convective heat transfer. Cannot be seen again, so I might as well use the original slide. So for liquid metals, the primary reason behind or rationally why liquid metals are being used, it's because of their high thermal conductivity. And actually, due to this high thermal conductivity of these liquid metals, they will also, as expected, have high heat transfer coefficients. So if they have high heat transfer coefficients, then of course, the rate of heat transfer will be higher. Now, based on the formula, the fundamental formula that we are using for convective heat transfer. Now, the first formula that you could see on the slide, the Nusselt number, which is being equal to HL, the heat transfer coefficient, the diameter, and the thermal conductivity of the fluid, which is this time also equal to the product of 0.625 and the Pecklet number raised to 0.4. I have not written it here, but this will only work for turbulent flow and for scenarios wherein the length to diameter ratio is greater than 60. And another condition that has to be met is that your Pecklet number should be from the range 100 to, in this case, 10,000. So this is for your turbulent flow in pipes. Now, this one. The second Nusselt number that you are seeing here, though you can read it also in Gen 2, please, is applicable for instances wherein there is constant wall temperature. So this one, the second one. But our main checking or testing whether we can use a particular formula for convective heat transfer is really the flow regime. So we need to test first on what particular flow regime our fluid is classified under, then whether it's laminar, turbulent, or transition, then we use the appropriate formula for that. So having said that, oftentimes this is the most commonly used formula for Nusselt number that would lead to the heat transfer coefficient that we are using to determine either heat transfer rate or heat flux. Okay, so this one, the second one, as I have mentioned, is only for constant wall temperature condition. Now, the use of liquid metal specifically finds its application in nuclear reactors. Okay, so they are used as heating mediums. Now, and to illustrate the use of this particular formula that you are seeing on top, so let's have the sample problem also taken from Gianco, please. So a liquid metal flows at a rate of 4 kilograms per second through a tube having an inside diameter of 0.05 meters. You have to be very observant when you read problems in unit operations because there are informations that a particular statement already specifies. So in this case, class, you are simply given a liquid metal. So the identity of the liquid metal is unknown. So primarily that would be a challenge if the physical properties of this particular liquid metal are not provided. But in this case, I'd like to emphasize that since its identity is not known, John Kuplis already provided it for us. If not, then it's impossible for you to solve such a problem because you can find its properties in your chemical engineer's handbook. And at times, that's also one of the reasons why the problems given in the board exam are not hindi siya pwede ma-solve, not solvable. It's because of the properties that is nowhere to be found because the identity in the first place is not specified. So let me continue. So the liquid enters at 500 Kelvin, referring to this metal. and is heated to 505 Kelvin in the tube. So take note that this time, the liquid which has already high thermal conductivity is heated. So it's being heated, so from 500 to 505 Kelvin. So the tube wall is maintained at a temperature of 30 Kelvin above the fluid bulk temperature. Another phrase in which you should also be very observant. The temperature of the wall, which is kept constant, is not given as a constant specific value, but rather it says here 30 Kelvin above the fluid bulk temperature. And it is not to be misunderstood as the temperature of the wall itself, but rather it's above the bulk fluid temperature by this amount. Now, heat flux is also maintained constant. So you are to calculate the required tube length, and that would be the L. And since, again, the liquid metal is not specified, so you're given its physical properties here. So those are viscosity, density, and heat capacity. So let me share with you Jumpboard so that we can write our solution for this. Okay, so we will write for this problem our given first. Okay, so we have here okay, and then we have the liquid metal here. Okay, so this is our then you have the mass flow rate. If possible, class, if you can get a soft copy of John Q, please, so we'll have an interactive discussion here. Please do so. I will try to check next week if we have. That way, you can provide the information, and I can check also if your understanding of the problem is complete based on what it provides. Okay, so this would be the, in this case, this is the inlet temperature of the liquid metal. The outlet temperature is 505 Kelvin. And then you're given the internal diameter or the inner diameter of the tube, which is 0.05 meters. And I'd like to write here that the wall temperature is 30 Kelvin above the bulk temperature. So we represented our bulk temperature in our fundamental formula for convective heat transfer as T. That's the bulk temperature of our fluid. Then it's mentioned in the problem that our heat flux is constant. Okay, now you're given also the properties of the fluid. So I'll just write them all in here. Then you have the density. Then we have the heat capacity or the specific heat capacity. I think I need to erase this one here. This is just joule. So this is just joule. And the another one, we have the conductivity. By the way, these are properties of your liquid metal whose identity is not specified by the problem. So you are required to find the length of this tube. Okay, now we go to the solution of this problem. So if we go back to the previous page, based on the information that you are provided, these are the information provided to you, and based on the required information, what do you think will be the starting formula that I'm going to write? That way it will lead me to the unknown, the length of the pipe or the tube. What formula would that be? You may write your answer on the chat box if the microphone is not available at your end. So what formula would lead you to the length of the tube where your liquid metal is flowing to? Um, Drexel, what do you think is the formula that will lead us to the length of the tube based on what you just learned in the past or what was discussed last meeting? Anyone? What formula would lead us to the length of the tube? A formula that you should be well familiar of because we have already discussed it at the start of convective heat transfer. What formula would lead us to the length of the tube? Okay, dear, what formula is that? Let me see, chat box, nobody writes. There's no direct formula that gives you right away the length. But if you recall the fundamental formula Q is equal to HLA times the driving force, the temperature difference, let's say, of the wall and the bulk fluid, or vice versa, if we just want the magnitude of this. So we change the way we take the difference of these two. That way we can get a positive answer because we're just concerned with the magnitude of the Q. This will lead you to the length. There's no direct formula for the length, but this will lead you to the length. Now, I'm already giving you a hint. How will the area give you the length that we're going to find or that the problem is asking from you? How is it going to give you the length, the area? Am I alone here? Third year? Thank you. So there's one in here. Length times width, miss. So in the case of a tube, if it's length times width, what's the exact formula for the heat transfer area when we're talking about the tube? Should it be the lateral surface area of the tube? Pi dl. Thank you, Jericho. Very good. So the area that we're looking for in here actually will be coming from the formula pi dl. I always start, if you notice class, I always start with a working formula which I can use to solve the problem because the way the solutions in any book for that matter is presented is already complete in the sense that the author who made such a problem already has the entire idea of what he's going to look for because he's the one who made the problem. In your case, if you're a student, you don't know how you're going to find the unknown unless, of course, you start somewhere. And this is what I always suggest. You think of the area, or rather you think of the formula where you can get the unknown information and the problem. And if we have to think of it in our case, in this particular topic we're discussing, so far the formula that is so fundamental in basics is this one. And you have to think, will it really lead me to the unknown, which is the length? And actually, the answer is yes. But I said, a while ago that it does not give you directly the L. It will just point you to the L. Now, since this is where the area is where we can get the L, you will label this as equation number 1. And you will try to find in this particular formula what you know and what you do not know. Okay, now let's go to what you know and what you do not know. Do you know the HL for now? Do you know already the heat transfer coefficient at this moment when you wrote this formula, or does the problem give you the heat transfer coefficient? The answer is no, the problem does not give you this because in the first place, thank you, Jericho, you're still going to determine this. When are you going to determine this? You're going to determine this after you have already established the flow of your fluid. So number 1 is write the formula. Number 2, establish the flow because the flow will lead you to the heat transfer coefficient. So I will not put a check in here because you need to find this one. Now I'll go to this one. We have defined the T sub W as the wall temperature, and we have defined the T as the bulk fluid temperature. Now, if I will ask you, does the problem give you the wall temperature? Does the problem give you the bulk temperature of the fluid? Yes or no? Is the problem specifying the wall temperature and the bulk temperature of the fluid? The answer is this is our given. I'd like to, okay. Drexel, you mean to say that the problem gives you specifically the wall temperature and the bulk temperature, Drexel? The problem actually does not give you the exact value of the wall temperature and the bulk temperature. But as what we have written here in our given, I wrote here the wall temperature is 30 degrees above the bulk temperature. So this 30 Kelvin, rather 30 degrees, I mentioned 30 degrees. This 30 Kelvin that is stated here is actually already the difference of the wall temperature and the bulk fluid temperature, because it says here, whatever is the value of the wall temperature, it's 30 Kelvin above the bulk fluid temperature. So going back to my question, the answer is a no, but the problem gives you the value of this already. This comes in the form of the 30 Kelvin value stated. The 30 Kelvin value stated is already the difference between the wall temperature and the bulk temperature of the fluid. So now, for me to be able to find the A, I need to find the HL and the Q. Okay, so I need to find these two. Now, since always we start with the working formula and then we establish the flow regime, if we are to establish the flow regime, we are to find the what in this case? If we are to establish the flow regime, we are to determine the what? The Reynolds number. Okay? So the Reynolds number. So thank you for that lesson. So if you write the Reynolds number, this time class, I will be giving you a different formula for Reynolds number for our liquid metal. And that formula is the inner diameter times the fluid mass velocity divided by the mu. Okay, so as for the inner diameter of the pipe, that would be 0.05. Now, this mass velocity of the fluid is actually its mass velocity divided by the cross-sectional area in which this particular mass is flowing into or passing into. So specifically, this D class, if I will write it in here, will be, for now, I'll write here mass flow rate divided by not the lateral area, but the cross-sectional area of the tube. Now, as for the mu, it's given already to be 7.1 times 10 raised to negative 4. So Pascal seconds. So I will not anymore write the unit. Now for this one, for the mass flow rate and the area, and I like to use a different font. For the mass, so the problem already gave us the mass flow rate to be 4 kilograms per second. So I'll write it here 4. And for the area, we'll have pi d squared over 4 because we want the cross-sectional area. So the cross-sectional area is pi d squared over 4. So the same diameter, which we will square and divide by 4. Whatever is the value of this, that should be multiplied to 0.05 and the product of the two divided by this, resulting to a Reynolds number. So your Reynolds number here is 1.435 times 10 raised to 5. So true to the introductory discussion of Jen Couplis, liquid metals always are used when flow is turbulent, and it expected that flow would really be turbulent. So with this Reynolds number class, we can conclude that it's already turbulent flow, that it is really turbulent flow. So if it's turbulent flow, then you can use the formula that was shared in the slide a while ago. So in that formula, let me write the formula. You're given that the Nusselt number is equal to HLD over K, and it should be equal to 0.625 times the Pecklet number. So this is the first time that the dimensional number, the dimensionless number, Pecklet number is used in one of the solutions of the problem. Okay, so you have the Pecklet number. Now this Pecklet number class actually is the product. So it is the product of the Reynolds number and the frontal number. Okay, so in here, you need first to find the Reynolds number. We have it already. Then next would be the frontal number. So I will go back to this formula after I have determined already the frontal number. So this is our equation 2. So let's go to the next page for us to be able to solve for the frontal number. So frontal number, you know already, is given by the formula heat capacity times the viscosity over the thermal conductivity constant of the fluid. So you have 120 is given times 7.1 times 10 raised to negative 4, and you have the thermal conductivity, which is 13. So this will give you an answer of 0.00655 for your frontal number. Now from equation 2, so that would be from equation 2 here, we will derive a formula that would lead us to the heat transfer coefficient. So from 2, so we can directly substitute, we can get that HL is equal to 0.0625 times the Reynolds number times the frontal number. We raise this to 0.4. We multiply it with the thermal conductivity constant, and everything here will be divided by the inner diameter. So that will lead us to HL. So substituting everything, so Reynolds number is 1.435 times 10 raised to 5. And we have the frontal number, which is 0.00655. The product of these two should be raised to 0.4. Then the K is 13, and we divide this entire product of these terms by 0.05. Now it gives you the HL, the heat transfer coefficient, which is 2,512 watt per square meter per Kelvin. So this is the HL already. Okay, the HL that we need in our equation 1. So now I will check this already. So I have this known. And this is known already as 30 Kelvin, the difference of the two. Then the next thing that would be determined is your Q. What is the Q? Now let me ask anybody here, what do you think will be the Q that you will equate to this expression here? That way you will be left only with the A. What is that Q? Q is, so it's fundamental actually. It's a fundamental formula that was learned probably introduction in chemistry down to PChem, down to thermodynamics. What is that Q that you will be using? You can write in the chat box, or what is that Q? MCP delta T. So thank you, Jericho. It's fundamental MCP delta T. Thank you, Vincent and Drexel. So MCP delta T it is. So we write MCP delta T. So I will now write the mass flow rate of the fluid, which is a 4. Its specific heat capacity, which is 120. And what is the delta T that you will use here? Remember, this Q is the amount of heat that is being transferred to your liquid metal. So what is this delta T? Will this be the 30 Kelvin or it will be a different thing? That would be 5. Correct, Excel. That would be 5 because this delta T class actually is the final temperature minus the initial temperature of your fluid, so that it will be able to, you will be able to account for the amount of heat that was transferred to it. So now we will substitute values. So you have 4 times 120. Specifically, this is 505 minus 500. Just like Drexel said, that should be 5. So your answer for your Q is 2,400 watt. Okay, so your Q, your HL, and this difference is already checked. So that leaves us with the area. So this is already known. So we can go back to equation 1 and determine the A. Wait. Okay, noted, Patrick. So now we'll have, so from the fundamental formula of convective heat transfer from equation 1 that we wrote, area then is equal to Q over HL times the TW minus T. Okay, now I will have 2,400 watt here. I will have HL, the HL that we got from this one, 2512. And this one is 30. The difference between the temperature of the wall and the bulk fluid, the difference between the two. So your area here will be 3.185 times 10 raised to negative 2. I think it's forthcoming now. What would be the next part in here? You already have this area. And I have started with that particular question a while ago. So area is the lateral area of your tube. So whatever is the area value that you got in the previous page, and that's 3.185 times 10 raised to negative 2, you equate it to pi times the d, which is 0.05 times the length. This should give you the length of the tube to be 0.203 meters. And this is the thing that the problem requires, the length of the tube. Okay, now let me go back to the given. So this is our given. This is required, and these are our solutions. Okay, any question for now before I go to the last sample problem? I think there's none. So let's go to the slide, go back to the slide and show to you the last problem. Okay. Now, our last problem here talks about the use of the log mean temperature difference. Let me see if I can show to you the entire one. Oh, thank you. So the log mean temperature difference. Now, when a fluid glass is, of course, flowing inside the pipe, and there's another fluid outside that is flowing either counter current to it or co-current to it, there's a corresponding difference in the temperature of the fluid that enters the pipe, and there's also going to be a corresponding change in the temperature of the fluid that is flowing outside of the pipe. These two temperatures, the difference in these two temperatures, actually, if you're going to get the difference, delta T, will be changing as the fluid moves through across the pipe, or rather not across, but along the pipe. So at the beginning, this will be the difference, but towards in here, the difference will be bigger. That's in the case when your temperature, when rather the flow of the fluids in your two concentric pipes are counter current, the sugat anay, kung sa aton language. If it's the case wherein you have co-current or parallel flow, meaning they are all entering in the same side of the pipe, this would be your temperature difference profile. But in these two, if you look very closely, whether it's an A or a B condition, a countercurrent condition, or a parallel condition in terms of the flow of the fluids in two concentric pipes, the delta T changes. So it's not something that is constant all throughout the length of the pipe. The same thing here with letter B. Wait. Excuse me, Miss Gautod-utod ka. Yes, because my internet is unstable at this very time. So anyway, let me go back. So if we have fluids flowing through concentric pipes, one being heated by another or one being cooled by another, the temperature difference profile is not constant. So that's the main principle that I'm going to state and emphasize here. The delta T difference is not a constant. As you could see here, whether we have counter current flow or we have parallel flow. And to compensate for that difference, or shall I say varying delta T, temperature difference of your fluids as they flow along the pipe length, we have to change the delta T formula, the delta T mean, which is just a simple difference of the temperature of the fluids, by what we call as the delta T lug mean. The delta T lug mean will now replace the delta T mean that is written in the original formula, fundamental formula that we have for convective heat transfer. So question is, when will we use this particular formula? You will use this when your fluids are flowing in concentric pipes. So it could be a bundle of pipes class. In the case of heat exchangers, you have a bundle of pipes and there's a shell, and then there's a fluid that is flowing inside the shell, and there's a different fluid that is flowing also inside the bundle of tubes. Anyway, we will go to that specifically when we touch already heat exchanger. So you will have to take into consideration the changes and the varying difference of temperature of the fluids that is flowing or that are flowing in your pipes. And that temperature would be this. So let me annotate your original formula then for convective heat transfer, which is Q equal to UA delta T mean. Oh, it's not written as delta T mean, but simply delta T, which is just a difference of the temperature of the wall and that of the bulk fluid will now be changed to, you just change this delta T to delta T log mean. Okay. It is very important, class, that you understand when you use this formula and when you use this. Now, especially when we talk about exchangers, heat exchangers, in which you have a bundle of tubes or we have two concentric tubes, you have to change the delta T mean here which we have been using and which we have been accustomed to at the start of the topic, to delta T log mean. Okay, you have to change it to delta T log mean so that we can account for this varying temperature difference profile for your fluids flowing inside the pipe and outside of the pipe. I think I have overly emphasized that already. Okay, so to illustrate the use of the delta T log mean formula, in the formula, in the standard formula that we have for convective heat transfer, let us have this, this particular sample problem. 15 minutes. Okay, I can do this. We can do this, class. So that's the temperature log mean difference. So a heavy hydrocarbon oil, which has a CP of 2.3 kilojoule per kilogram Kelvin, is being cooled in a heat exchanger. So it's now talking about heat exchanger from 371.9 to 349.7 Kelvin and flows inside the tube at a rate of 3,630 kilogram per hour. A flow of 1,450 kilogram water per hour enters at 288.6 Kelvin for cooling and flows outside the tube. So you can imagine that you have a bundle of tubes, and this bundle of tubes, class, is housed inside a shell. In your shell, you have the cooling fluid, and inside the tube, you have this hydrocarbon oil, which needs to cool down. And for it to cool down, you need this water, your cooling medium, that flows in the shell, in the annular space between the shell and that of the bundle of tubes, so that this particular hydrocarbon oil will cool down. So you are required here to determine the outlet temperature of the water, specifically the outlet temperature of the cooling water, and determine as well the heat transfer area, given that the overall heat transfer coefficient based on the inside dimensions of the tube is equal to 340 watt per square meter Kelvin, and that the flow is countercurrent. Letter B is just asking for the same thing, but this time the flow is parallel already. So what is important is we illustrate the use of the log mean temperature difference. So let me just go back to our Jumpboard. So let's start with the new page, and we will write the given information for this particular sample problem. When you have actually a shell and tube, it is something like this, class. So it has several passes there. And in here, this is your bundle of tubes. It could be something like this, or it could be simply arranged like this. That will be shown to you in detail when we go to heat exchangers, the design of heat exchangers. By the way, the arrow should be the other way around. Okay. Okay, so this is your water, your cooling medium. Let me go back to my solution here. And for this water, you're given a mass flow rate of 14,500 kilogram per hour. Let's say we have the CP of this water. It's not given in the problem. We'll just use the standard CP of water, which is 4.187 kilojoule per kilogram Kelvin. You may also use the CP of water at the indicated inlet temperature of the water in here, which is 288.6 Kelvin. So what I'm trying to say, class, is you may use the standard CP, or you may use the actual CP of the water at this particular indicated temperature. Anyhow, your answer will not vary that much. Now, for water, the temperature, the outlet temperature, let's say this is T sub 1 is unknown, and this is T sub 2. I will explain later the labeling of the temperature based on the profile that we have in the PowerPoint slide. So we have a T sub 1 here for the outlet temperature of the water, and we have T sub 2 in here. Now, I will use a different color here for our oil. The oil is flowing inside this tube, so meaning it lives here. Okay, so this is your tube, okay, which I have drawn. And this one, the outer two lines are the shell that houses your bundle of tubes in here. For your hydrocarbon oil, I like to place it as hydrocarbon oil. Your CP for this, I'll just place here an O for the oil, is 2.3 kilojoule per kilogram Kelvin. And you're given the mass flow rate as well of the oil, which is 3,630 kilogram per hour. Okay, now I will change color first. This one is for the water. Okay, now I think I have placed everything here. Temperatures. Okay, so temperatures, I have not placed the temperature of the oil. The inlet temperature of the oil, we use already T sub 1 here, so this would be T sub 1 prime. Your T sub 1 prime is 371.9 Kelvin. And I use already T sub 2 here, so this should be T sub 2 prime. And that would be 349.7 Kelvin. So the red are the data for your hydrocarbon oil. The black thing is for your water. So as for the required information, let me borrow your few minutes later. So for your required information, you have the T sub 1 and the area. If you're given the overall heat transfer coefficient U sub I to be 340 watt per square meter Kelvin. And the flow is counter current. Counter current flow. Okay? Now, same premise class, same premise. Solution. Question, big question. What formula will I use? That way I can find that T sub 1. It may not be a direct formula that will be reflective of T sub 1, but it should be a formula where I can start with. So we have Q equal to UI AI delta T log mean. Okay, before we use delta T mean, now we will use delta T log mean. In this formula, I know this, it's given already. This one will point to me the T sub 1. I need to find this so that the remaining expression would be this one only. So next that I need to find is the Q. But before I even find the Q class, let me just go back to the slide because I forgot to tell you why the representations of the temperatures are like this. You have T sub 1, T sub 2, and you have T sub 1 prime and T sub 2 prime. Okay, let me just for a few seconds go back to the slide and show to you the profile for counter current flow. Okay, this is the profile for counter current flow. So this is for your cooling water. So from a lower temperature to a higher temperature expected because heat is going to be transferred from your hydrocarbon oil to it. So lower temperature to higher temperature. And this one is for your hydrocarbon oil. From a higher temperature, it needs to cool down to this low temperature T sub 2 prime. So the labeling of our given is based on this profile that is given in Jan Kuplis. Other books may have a different representation, but this one, I'm using the representation of the book itself, where the sample problem came from. The delta T1 and the delta T2 that you see in the formula represents the difference of these temperatures of the fluids that is flowing through or along your tube or your pipe. Okay, so for parallel flow, this is how we label it. So and let me now go back to our Jumpboard. Okay, so we have this and we're here. So I said a while ago, I need to find the Q. That way, what is left is the delta T log mean, and I can find right away T sub 1 from that. Again, so think, what particular formula that I know already would lead me to the Q? The Q, which is, okay, thermodynamics, again, mCp delta T. So mCp delta T. But question, which mCp delta T will I use? That of the oil or that of the water? I think common sense will tell you that it should be of the oil. Should be of the oil. It should be of the oil. What? Because the delta T of the water in itself is not complete because we don't know its outlet temperature. So this Q is also actually equal to the Q of the water, which is M of water, CPW of water, and delta T for water. So they're all equal, and they're even equal to this one. So I will find now, or so as to save us some time, I will directly equate the mCp delta T of oil in here so that I will be left with the delta T log mean. So for the mass flow rate of the oil, we have 185. Sorry. Mass Cp of the oil is 3, and you are in a hurry. Okay, mass flow rate of the oil is 3,630. I will not anymore write the units. Its Cp is 2.30. Anyway, it's written already before. And then the change in the temperature of the oil is given by the difference of 371.9 and 349.7. This thing class is the Q sub O in here. We will equate it to UIAI. So your UI is given in the problem to be 340. The area, AI is something that we do not know. And we have here the weight class. The AI, I got mixed up with the paper that I have. Sige. So we can go straight to AI. In that case, we'll be needing it, but just like the Q of the oil being equal to the Q of the water, as I have mentioned a while ago, you can get the T sub 1 of the water in here. So I have mass flow rate of the water, 1,450. Its Cp, which is 4.187. And the delta T, which is, so since we're equating class values only, we're not concerned with the sign. So we'll have the higher temperature of the water, T sub 1, minus its inlet temperature of 288.6. So if I'll get the T sub 1 in here, I can find the delta T lube mean. So in here, you can get the T sub 1 to be equal to 319.1 Kelvin. Okay, that's it. Now, I think I missed something to write. I missed writing something. It's also asking for the area. So we need to find the T sub 1 of the water and then get the area. So that is why when I write the UI a while ago, I cannot find it because it's one of the unknowns. So I need first to find the T sub 1. That way I will be able to find the delta T lube mean. Okay, so we'll get the delta T lube mean for parallel flow. And that would be delta T2 minus delta T1 over the ln of delta T2 over delta T1. Now, as for the formula for countercurrent flow for delta T2, this would be T2 minus T2 prime. And you'll have here T1 minus T1 prime. And you'll have here the ln, the same thing, plus T sub 2 minus T sub 2 prime, T1 minus T sub 1 prime. If we will substitute values so as to save us time, we will substitute all the values here, including the T sub 1 that we got out of equating these two relationships here, the Q's of the oil, the amount of heat transferred from the oil to the water. Your delta T lube mean is 56.9. So knowing your delta T lube mean, any of the Q values that you have here will do for determining the AI. So for that matter, we can have mass CP delta T, let's say, of oil. This time would be equated to UI AI delta T lube mean. This is our actually equation 1. So if we would do that, the mass flow rate of the oil your 3,630 kilogram per hour for the oil, your CP, which is 2.30, and the temperature difference, which is 371.9 minus 349.7. The value of this class actually is 51,490 watt. This 51,490 watt for the oil, actually you can use also that of water. It's the same value that you will be getting. You equate to our equation 1. So we'll have 51,490 watt is equal to, so your UI 340, you have the area, and then you have the delta T lube mean, which is 56.9. This is from equation 1. So in here, you'll be able to get the area, the inner area or the inside area of the pipe. Total that is with a value of 2.66 square meter. So the only difference of this solution with that of letter B class is the formula in determining the temperature lube mean difference. So amo lang nang ila kinalain. But the same principle, the same formulas will be used in finding the area. Okay, in finding the T sub 1, the same procedure because this is a known fact even since your Chem days or chemistry days. So there's one here that somebody will CP data. Okay, I was not able to read it. So this is it, class. I leave to you letter B to do on your own as an exercise. That way you will be able to see the difference between the heat transfer area for counter current flow and heat transfer area for parallel flow. If you have a copy of Janku, please is explained there why the value that you are getting is, let's say, higher or lower than this value. So make sure that the validation or the comparison of the two values and the learning behind the comparison you're able to read, because it's very important. So this now ends our topic on forced convective heat transfer. Tomorrow, I will start with natural convection. So any question for now? I've used 4 minutes of your time. Any part in here in the solution? It's not clear. So if there's none, I will stop sharing now. And I will end recording. Everybody has written their names here on the chat box for the attendance. Ginto Vergavera Gintos. Nibet Millares Sumaning. Apostol Villarosa. Daniel Amit. Okay. Okay.
Miss,
Yeah.
question, Miss.
Yes.
Bali, Miss, ang quiz, Miss, ang force
Ah,
convection, Miss. Asta diri, Miss, or...
Astadere. Included ni siya.
Okay, Miss. Thank you, Miss.
So anyway, it would still be on Thursday pa man. Okay, tomorrow, maklas pa kita. So we will just meet on the 1:30 to 4:30. I will just message Renda later. Okay? Sige. So if there aren't any questions, let's call it a day for now for our course. Bye for now, class. Have a good day ahead.
Thank you, Miss.
Okay.
Miss.
Thank you as well.
Thank you, Miss.